Okay. Is it time? Should I share?
Yeah.
Okay.
Tim, you can tell me when we're recording live so I can go.
Good to go.
Hi, everyone. Welcome to the sixth Cats4AI guest lecture. It's our pleasure today to have David Spivak with us. He's a research lead at Topos Institute, spent a lot of time at MIT, and he's one of the main figures bringing a lot of category theory ideas into science and technology. So we're quite excited to have him with us today. And today he's going to be telling us about dynamic organizational systems. So from deep learning to prediction markets. Yeah, take it away.
Okay, thanks. Are things blocking my screen or can you see okay?
We can see it okay, yeah, and even your cursor, yeah.
Okay, great. Okay, so yeah, so for a long time, I didn't call it this, but for a long time I've been interested in applying category theory to sense making. So what I mean by sense making is that living things like us get a sense of the world, whether it's a cell or a person or even say an organization, they get some kind of sense of the world, but how is this sense structured? All of our senses are constructed, right? That somehow our bodies have to make these senses for us. And yet, like, you know, how should you think about that? So you could imagine the structure as a database, for example, and that was an early way I thought maybe I could just start on this project. And then if you want to create collective sense, like if you want a bunch of things to communicate and create a sense together of what's going on, then maybe you could use something like data migration to move the way that I see the world structured as a database to the way you see the world. And like we could share examples and things like that. But I got interested in like the dynamics itself. How does the data flow through these systems? So I think it was 2019, there was an adjunct school, category theory adjunct school, and I ran a group called Towards a Mathematical Foundation of Autopoiesis. Autopoiesis is basically how things can create themselves in the world. A cell or a football team or a political party or whatever. And so my group with Brendan Fong as the TA included David Jazz Myers, Sophie Lipkind, Bruno, and Toby Smythe. And we did some work on, like, we had some insights into lenses and learners and categorical systems theory, but autopoiesis itself remained mysterious and still does. But what I was working on is not so much how does it work, but like what language would you be able to give an account of this? What math would let you express these sorts of systems whose internal structure adapts? So my goal is to create that mathematical language, or with as many people who want to help as possible. And today I'll tell you about my progress so far on that, because it does kind of move into the deep learning, machine learning part of the world and include more things. So Eugene Wigner wrote an article where he lauded math as unreasonably effective in the natural sciences. And I think that many of his assertions also would affirm the effectiveness of category theory in math. It's somehow there's some kind of like overwhelming effectiveness that you get used to math and you see like, oh, this is helping me make progress in things that I find unexpected. He also happens to mention the ability that is our ability to make the miracle that's our ability to make sense in the world. But I think that maybe the real miracle, I don't know if it's a real miracle, but abstraction is such an amazing thing. And so it's a bidirectional thing. And in some sense, it's like a polynomial, it's a map of polynomial functors or a lens. So what is abstraction? You take a complex situation with a lot of moving parts or something, and then you boil it down to a simple one. And you can imagine that as a function from A to B, the complex world simplified to some just very basic thing, B. But then the point is not just to make that analogy in the forward direction. The point of abstraction is that once you abstract the thing, then you can look at conclusions about that abstracted thing, f of A, and take those conclusions back to the specific situation you started with. Because since you remember the specific situation you started with, and you remember things you can do with the abstraction of it, you can then conclude things you can do with the original situation. So that's basically what a polynomial functor map is. If you think of polynomial functors as like situations and things you can do with them, or positions you can be in and directions you can move, then a map of polynomials will turn out to be this abstraction in this sense. But I think category theory is unreasonably effective in math, and I think that poly is actually unreasonably effective in category theory and also in computer science. So this category poly is strange a bit. I mean, it's kind of how, if you understand lenses, it's got that strangeness, but it's still pretty easy to think about. Like, you get used to it, and it's not like a triple category or something where you're just like, I personally have trouble managing all the different directions of things. But poly is just very set based, and yet, and so it's pretty easy to think about, and it's really all about plumbing abstractions in the above sense. You just plumb abstractions into each other. And it's got tons of structure. For example, it's got all limits and co-limits. Now, in category theory, the more structure a category has, the kind of more you can play, more fun things you can do with it, right? So there's limits and co-limits. There are 3 orthogonal factorization systems, which let you factor maps. There are infinitely many, not only infinitely many monoidal structures, but infinitely many monoidal closed structures. I've been interested in 2 of them, but there are infinitely many. There are various co-closures, like instead of monoidal closure, there's a monoidal co-closure. For example, the comonoids in poly are exactly categories. The monoids generalize operads, et cetera. So it's like, why would you find all of this stuff in one category? The category of sets or a topos or something like that has some nice things. It has a subobject classifier, et cetera, but it doesn't have 3 orthogonal factorization systems and infinitely many monoidal closed structures. And the point is that those things are telling us that poly is just kind of extremely rich, and there's lots you can do with it that don't feel like you're inventing them. It feels like you're discovering them. It feels like you're moving through very clear pathways between very different ideas. So it's also got tons of applications in computer science, and that's more relevant to this talk. Things like Moore machines and Mealy machines, but also databases and data migration, algebraic data types, bidirectional transformations, which you guys have been talking about here, dependent type theory, effects handling, cellular automata, rewriting workflows, deep learning. So I'll be focusing mainly on deep learning today. Not so much focus there, but like that's the kind of thematic direction. But there's just lots of parts of computer science that are touched by polynomial functors. So today I'll be talking about dynamic organizational systems, and that's because one interesting thing you can do with poly is think about dynamic interactions. So if you look at that picture there, you see some things wired together, and you can imagine that in each box is a dynamical system, something that's kind of changing its internal state based on what's flowing into it, and then communicating something about its internal state outward through the wires flowing out of it on the right. So it's kind of like you could imagine you're hearing stuff from me right now through your ears, and those would be the ports on the left. That's changing your internal state, and then maybe you're moving your eyes around, or maybe you're doing something, and the position of your body is changing. So, but in this picture, you see it very static. It's a static wiring diagram. But what if you imagine P1 outputting the phrase, I want to disconnect from P3? So that's the kind of thing that you might do in a pi calculus or something like this. But what I'm doing here is very much, what I'll be talking about here is very much using only the structures that exist in poly. There's nothing kind of invented. It's more just discovering what's in poly and then using it to do interesting things. So what I want to say is that here we're imagining that the flowing signals, the stuff that's flowing on the wires, can induce changes in the wiring pattern itself. And that's what we're going to talk about with polynomial functors. But for example, in training artificial neural networks, the flowing signals, like the training data that flows through the network, changes the network itself. It changes the weights and biases. So in the poly ecosystem, as I said, there are native data structures for that. And so there's a monoidal double category I'll be talking about called org that's well suited for this. Artificial neural networks have another property, namely there's a kind of coherence that comes from the chain rule. So basically the composite of gradient descenders is again a gradient descender. The same thing is happening in all the neurons of your neural network. So Brandon Shapiro and I call these things dynamic organizational systems, and they include things like artificial neural networks, prediction markets, Hebbian learning, and other things. And so that's what I mean by dynamic organizational systems. So today, during the remainder of the talk, I'm going to give an intuitive mathematical introduction to Poly. And mainly the reason for number one is I want to tell you that polynomial functors fit into the computer science ecosystem. Like they're a major part of how things work, even if people haven't identified all of, like, haven't named for themselves how many of the things that they're doing are just polynomial or like natively working in polynomial functor land. But once I do that, then I'll talk about the monoidal double category org, define dynamic operads and dynamic monoidal categories, and give the example of artificial neural networks and prediction markets, and then finally conclude with a summary. So in this first part of the talk, section 2, I guess after the introduction, the point here is to talk about polynomial functors so that you can see that these things are a major part of computer science. I'm not going to talk about everything, but that they do, but give you a flavor so that you know, like, if you implemented polynomial functors in some kind of DSL, then you could use them not only for machine learning, but for other aspects of your workflow. So let me first give you the definition and intuition for it. So a polynomial P, you should basically think of it as a data structure. I mean, so it's going to be all positive things with like, basically there are sets, coefficients could be sets. So this set 3 really, this 3 really means the set with 3 elements, and the exponents are sets also. So everything's going to be positive or non-negative. But this algebraic expression, y squared plus 3y plus 2, corresponds to the 6 summands here. 1, 2, 3, 4, 5, 6 correspond to the 6 dots down there. And over this dot are 2 dots corresponding to the exponent 2. Over these 3 dots are 1 dot corresponding to the 3 exponent 1 things here. And over these 2 dots are a y to the 0 that I didn't draw here, y to the 0 meaning 0 dots. And so this is a kind of bundle view, like you have this bundle over this space. And here's a kind of corolla forest view, as though you have trees, but the trees just have height 1 right now. And so we have 6 trees, and one tree has two branches or 2 directions or 2 arrows. 3 of them have 1 direction, and 2 of these positions down here have 0 directions. But what are these pictures? Well, the easiest categorical description is that poly is the category of sums of representable functors set to set. Now, what does that mean? For any set S, this y to the s, kind of standing for Yoneda embedding, y to the s is the set of functions from S to blah, so to foo. This is the functor represented by x. If you put an x into here, you'll get the set of functions from S to x, and the cardinality of that will be x to the power s. So that's why this notation is good. So that's y to the s. This y squared means the set of functions from 2 to whatever. If you plug in 5, there will be 25 functions from 2 to 5. So a polynomial is just a sum of representable functors, and you add up as many of these representables as you want for different pi's. You just add them up, take the coproduct, and that's the polynomial functor. And a morphism of polynomials is a natural transformation between these 2 functors. One convenient fact is that I, this base here, this the indexing set of the coproduct, this I, the number of dots here, is this thing applied to 1. If you plug in 1, you get 6. And so P of 1 will always be the number of things in the base there. And the thing in the exponent I'm going to write as P bracket I. Okay, so there are many ways. So I want to give you intuition for this because I know a lot of people in the audience are not category theorists. So just imagine you have a polynomial functor, and okay, just think about it like this, one of these things, or think about it like this, a sum of representables. Now, what you should think of, there are 3 ways I'm going to tell you to think about it. One is that the positions here, are types. This is a type, this is a type, this is a type. And for every type, there's a set of terms. of that type. P bracket I, the exponent, is the number of terms. So this thing has 2 terms, these 3 things have 1 term, and these 2 things have 0 terms. Or you could think of I as the set of problems, and each problem has some number of solutions. 2 solutions, 1 solution each, and 0 solutions. Or you could think of I down here as the body positions of some kind of agent. So this agent can be in one of 6 different positions, but if they're in this position, they can receive a Boolean sensation, like they're either receiving through their eyes a true or false. Now these, I want to, and here they can only possibly receive one thing, and here they can't receive anything. So I want to say, by the way, that this, instead of the number 2, could be the set R to the million. It could be the set of pixel images. So when they're in this position, they're receiving a million real numbers. Instead of 2 things, this bundle has R to the million many dots in it. So there's different body positions you can be in, and for each body position you can be in, you have some sensorium or some sort of input space. So I want to now talk about polynomial morphisms. You've talked about lenses a lot. So let's say you have, this is very similar. So suppose you have polynomials P and Q. So y cubed plus 2y, and y to the 4th plus y squared plus y to the 0 plus y to the 0. And what is a polynomial morphism? Well, it kind of delegates or sends every p position, chooses a q position. So that's kind of like on the base. That's the get part of the lens. And then once you pick for each of your 3 p positions, you pick a q position, then you need to take all the q directions back to the p position you chose. So you say, okay, decision number 1 or problem number 1 will be abstracted to problem number 1 of q. And problem number 2 of p will also be abstracted to problem number 1 of q, etc. And so then once you say which problem each p problem is abstracted to, you then say how solutions to that q problem translate back to solutions to the p problem. If I need to, I'm going to just write this lens as like what's called phi1 and phi sharp. Phi1 is kind of the one component of the natural transformation, and phi sharp is kind of something that comes from the knit embedding, but it's not too important. It's just for people who are like trying to follow these slides in a serious way at any point if they want to. Those are notation I'll use. Basically, I'll just talk you through things. So anyway, forgetting this for just a second, the idea is you abstract. So a morphism of polynomials is you take all the problems in P to problems in Q, and for any solution to the Q problem, you return it to a solution to the P problem. But there are lots and lots of operations on polynomial functors. Plus, times, tensor, compose, internal Hom, left con extension, but lots and lots and lots of other ones, infinitely many, and there are infinitely many closed ones. For example, these 2 are monoidal closed. So given 2 interfaces, P and Q, there are many ways to get another interface. So I'll just talk about each one in terms of problems and solutions. So let's say you take 2 interfaces, P and Q. What is P plus Q? Well, a problem for P plus Q is either a problem of P or a problem of Q, and a solution is the solution. So you just add up like you can take, what are the problems of P plus Q? A problem is either a problem of P or a problem of Q, and solve it. If you take P times Q, a problem for that thing is a pair of a problem in P and a problem in Q, but you just need to solve one or the other. Dirichlet product, tensor product, a problem is a pair, a problem in P and a problem in Q, but you need to solve both. Substitution problem product, a problem is a choice of problem in P, and for every solution, a problem in Q. So it's kind of an ordered set of problems, like, or a dependent set of problems. So now how do you solve one of those? Suppose I had a problem in P, and for every solution to it, a problem in Q. Then a solution to that whole thing would be a solution to P. Well, that opens up a new problem in Q, and you have to solve that too. So a solution is a solution to P and a solution to the corresponding problem in Q. The internal Hom, PQ, what is that thing? Well, the problems there, a problem is to give a polynomial map. Every polynomial map from P to Q is a problem. And what's a solution to that problem? A solution is to give a solution, is to give a problem in P, and then you're going to get a problem in Q from that, and you have to solve that. So how do you solve a map from P to Q? You give a problem in P that you can solve in Q. The last one, this little vertical thing, is left con extension. I draw it that way because it generalizes lenses. The category of lenses is like its objects are these guys, and its morphisms are morphisms between these guys. But I'll say more about that in a minute. So here is just in case you want to stare at something kind of complicated. These are some formulas for P times Q, P tensor Q, P composed Q, and P internal Hom Q. Like I said, that the problems of this one are problems of P and problems of Q, and solutions is solve this or solve that. I said here you have to solve both, etc. So these are just kind of in case you wanted to see them all in one place. So yeah, the category of polynomial functors has a lot of, it's just coproducts of representables and the natural transformations between them. It's also the free distributive category on one object. So there's like kind of nice descriptions of it. And from the fact that the description is so easy, I think that's what makes it have so many amazing surprises. One I'll tell you about in a minute. But as I said, so this substitution product P composed Q means just plug Q into P. And this is one we'll be talking about a lot. So if you plug y plus 1 into y squared, you get y squared plus 2y plus 1. But of course, substitution is not symmetric. So if you plug y squared into y plus 1, then you just get y squared plus 1. So even though it's not symmetric, it is a monoidal structure, and the unit is y, because when you compose with y, when you plug p in for y, you get p. And when you plug in y into p, into the variable of p, you get p. But in any monoidal category, it's interesting to consider both the monoids and comonoids. So if you're ever in the presence of a monoidal category, it's worthwhile asking, what are the monoids? And what are the comonoids? And in the case of poly, the comonoids are exactly categories. So you've been talking in this series about categories, and the comonoids in poly are exactly categories. So if C is a category, why is that a comonoid? Well, if C is a category, then what ends up being important is for any object of that category, look at all the maps out of that object. Then the set of all maps out is like, you add up over every other object the maps from C to C prime. And so the associated, if you want to talk about a category as a comonoid in poly, you would, if you don't know what a comonoid is, I'll tell you in just a second. You want to think about this category as a comonoid. Well, it's going to be a polynomial with two maps. That's what a comonoid is. So the polynomial is going to be the sum over all objects of y to the power the maps out of that object. That is a polynomial, and that polynomial comes with two maps, a map to y, the monoidal unit, and a map from that polynomial to itself composed itself. And so these two maps, together with the polynomial itself, form what's called a comonoid. And they do so whenever C is a category. The unitality and the associativity of the category turn into the co-unit and co-unitality and co-associativity of this comonoid. So they're just the same structure, and it's just encoded in a kind of interesting way. And I know Connor McBride, for example, talked about this in a Topos Institute colloquium at some point, this kind of way of representing categories. But the point is that comonoids in poly are exactly categories, and yet maps between comonoids are not functors. They're these weird things that feel like lenses. They're cofunctors, where objects in C would go to objects in D, but morphisms out of those objects in D would return to morphisms out of the objects in C. So things kind of go backwards and forwards. And I'm going to denote the category of categories and cofunctors. In other words, the category of comonoids in poly by cat sharp. The objects are categories, but the morphisms are a bit sharp. They go weirdly backwards. So that's just notation I'll use today. So for any polynomials, P and Q, there's a last structure I haven't told you about, which is the left con extension. But this thing represents, some polynomial that you could read if you cared about it later. But if you have any two sets, for example, you can think of them as constant polynomials, and then AB will turn out, if you read this formula, it'll turn out to be the monomial by to the a. And maps between AB and A prime B prime, I don't use ST and AB, I just use kind of AB and A prime B prime, will be natural transformations. So what is a map from AB to A prime B prime? It's a get map on the base of the bundle and a put map on the total space of the bundle. So taking B and A prime, you can get an A. So in other words, it's a get and a put, and it is just this, like this is coming from left con extensions. But these come up, right, these come up in functional programming lenses, and you've seen a lot of them. But why will they be useful to us? They'll be useful to us because a map from SS to AB will be a Moore machine. So we're starting to get into the dynamics. So we're trying to get towards, what I'm trying to do now is tell you all about polynomial functors, but telling you about them with a view towards deep learning and other things that generalize deep learning. And the reason I'm doing that, again, is because I want to show you that polynomials are intuitive, even though they might be new, they are intuitive. You can get into, what I mean is you can get an intuition for them, thinking about them as abstractions or lenses or whatever. And that they will, soon I'll show you how much of computer science they kind of talk about. And I'm starting here with Moore machines because these are going to be dynamical systems of the sort that show up as deep learning systems are trained. So what is a Moore machine? A Moore machine is a set S that kind of updates and reads out. So you have the set S, and for every element of S, you can read out a B. So B is like some kind of interface. AB is like some kind of interface. For every state, you can read out a body position, and then given a state and an input, some kind of sensation, you get a new state. So what do Moore machines let you do? If you had an initial state and you had a list of inputs, A0 through N, then you could get a list of outputs. And how would you do it? The ith output would be the readout of the ith state. That's not so bad. And the induction on states would say that the I plus first state would be kind of the dynamics, what you get by taking the ith state and updating it with the ith input. So you take a state, you get an input, you get a new state, and you just do that repeatedly over a list, and you get a list of outputs. So I just said that a map from SS to AB is a Moore machine. A map from SS to the internal Hom, AY, BY, is what's called a Mealy machine. A Mealy machine consists of a set of states, and instead of two maps from S to B and S times A to S, you kind of combine them into one map from S times A to S times B. So whereas here, you can update the state immediately with a new input, but you have to use the current state to get a B. Here, you can not only update the state immediately with an S and an A, but you can also immediately use the input you got to get an output B. And these are called Mealy machines. And these are, again, just maps of polynomials from SS to something, AY, BY, the internal Hom. So I'm trying to show you that these, to some extent, I'm trying to show you that you can use polynomials to talk about Moore and Mealy machines, which are ways of thinking about dynamics in computer science. But I'm also trying to show you that various structures that exist very generally for polynomial functors, like internal Hom and left con extension, work in a very simple way when you just use constants. Constant polynomials S for the set S, and constant polynomial B or A for the sets A or B. Mealy machines, again, transform lists of inputs into lists of outputs, and we'll be talking about both Moore and Mealy machines going forward. So here's how you depict a Moore machine interface. If the Moore machine was like AB here, I'm going to denote that with A coming in and B going out. And if A happened to be a product like A1 times A2, and B happened to be a product, B1 times B2, B3, I would draw it like that. So if you see pictures like this in a second, just know that all I'm trying to do is denote these guys here, A1, A2, A1 times A2, B1 times B2, B times B3, etc. So now I'm going to save space, instead of using time symbols, whenever there's a times, I'm just going to concatenate. So this guy would denote the interface by to the a, by to the a here, or ab, same thing. And this guy here would be b1 times b2 times b3 times y to the a1, a2. So here's a picture of a wiring diagram. Maybe you've got some system where some input is coming in from the outside and controlling a plant or updating a plant, and that plant is sending some information about itself to a controller, which is then processing that and deciding what input to send the plant to control it. So the plant is being run by the external stuff and this kind of controller, and then the outside world is seeing the results. You could make this much more complicated if you want to, but I wanted to make it as simple as I could so I could show you the polynomials involved. The controller has outputs B and inputs C, so it would be this polynomial. The plant would be this polynomial because it has inputs A and B, and outputs C, and the system itself, the whole system, would have inputs A and outputs C. And so the wiring diagram, this picture represents a lens or a map of polynomial functors from control tensor plant to system, from by to the c, tensor cy to the ab, to cy to the a. So what we're saying is that a wiring diagram represents a map of polynomials. But every Moore machine, the controller itself, is also a map of polynomials from some sy to the s to by to the c. I don't know if you remember that, but basically that was over here. A Moore machine is a map from SS to AB. In other words, from SY to the S to BY to the A. So a Moore machine is a map from SY to the S to BY to the C for the controller, or TY to the T to CY to the AB for the plant. The wiring diagram itself is a map of polynomials. And so you can tensor these two things together and get SY to the S tensor TY to the T, which turns out to be ST, Y to the ST. You can then, once you've tensored these guys together, you could then get a map to the external thing, CY to the A. And so what is all that telling you? I'm not trying to overwhelm you with anything. What I'm trying to say is that if you had dynamics that are running the controller, taking a list of inputs to a list of outputs, and you have dynamics running the plant, taking a list of pairs of inputs to a list of outputs, and you had this wiring diagram, then you would be able to take a list of inputs for A and get a list of outputs for C. And maybe you would say, well, of course I can do that. I don't need all this fancy stuff to do it. But the reason that the polynomial functors are worthwhile is that every dynamical system, like this, gives you a kind of common formula where if you implement polynomial functors once, you don't have to keep doing that plumbing yourself. You can just run it very simply. So this whole story is lenses through and through. We don't need coproducts. So it's just lenses. We just have monomials. If you wanted more complicated things where you have mode dependence, where like when you close your eyes, the set of things you can see is different than when your eyes are open, where the types can change based on what's going on, then I call that mode dependence. And there you would use general polynomials. But the point is that there's just all these monoidal structures on even lenses, and we can use those to construct things like this, to make wiring diagrams. So I want to talk about how category theory is useful in computer science. So the simply typed lambda calculus is a base for functional programming. In Haskell, types are objects and programs are morphisms. And the simply typed lambda calculus is Cartesian closed, meaning you can tuple together different maps and objects, and you can make function types. And then side effects are handled by monads. But I think that Poly can add a lot to this story because, first of all, it's already involved in what I've said in a lot of ways, or at least in, so polynomial functors is a model of a simply typed lambda calculus, but it's also, because it's Cartesian closed, but it's also involved in Haskell and other like functional programming languages because algebraic data types are free monads on polynomial functors, or inductive data types are free monads on polynomial functors. The initial algebras and final coalgebras are very commonly used for like anamorphisms and catamorphisms. And then lenses, which are also used a lot in functional programming, are just the maps between monomials. But Poly goes far beyond functional programming. We've seen it's useful for state machines, like Moore machines and Mealy machines, but it's also useful in databases and data migration. There's just a very clean story about how that works using polynomial functors. It's useful in dependent type theory. effects handling, rewriting, workflows, and deep learning. So I just want to give you like this idea of unreasonable effectiveness so that you could say that is you might find as worth thinking about polynomials or even implementing polynomials so that you can kind of do all of these things in a common system and not have to switch between different systems all the time. So in functional programming like Haskell, you might see something like data foo y is bar y type baz y type some other stuff. Or for example, a more common one is that maybe y is just y or nothing. And these are polynomials like y cubed plus y squared plus 2, because we have this, y cubed plus y squared plus y to the 0 plus y to the 0, and y plus y to the 0. And they're polynomial in that they act on Haskell data types. Whenever you have a map of Haskell data types, you get a map from foo of the first one to foo of the second one. But there's another thing in Haskell you might see, which is like list A is nil or cons A list A. And what's going on here is that this is the algebraic data type corresponding to 1 plus A times Y. Now, you can't necessarily read that off. So you can read it off, but you have to kind of get used to it. Why this polynomial and this is the same thing. This Y here is kind of standing in the place of list A. But every polynomial like this one has an initial algebra and a final coalgebra. And the initial algebra of this polynomial is list, the sum over natural numbers of A to the power n, lists of A's. And the terminal coalgebra is streams. It's either a list of finite length or an infinite list. That's what you'll get by taking the terminal coalgebra. Now, these might sound like fancy words, but the point is like these words like algebra and coalgebra or monad and comonad or things like that, monoid and comonoid, are things you find in every monoidal category in category theory. There's tons and tons of them. And so people are very used to thinking about them, and there's like theorems that apply to all of them. And so the point is, if you can use those ideas and get used to them and then apply them in poly, you can get intuition for how they work using what you know about polynomials or what you know about lenses. And you can get an intuition for how poly works by using what you know about those things in other places. So it just helps you transport back and forth. And you know that they're not only that, but they're very well working objects throughout mathematics. So you can have some faith that they will be well-working things in polynomial functor land also. As another example, databases are used throughout computer science. A database consists of a schema, the things and how they relate, as well as data, which are examples of the things and those relationships. And so one nice category theory story for this is that a schema is a category and the data is a functor from that category to set. And then you might want to move data around from one schema to another. And a really useful way of doing that is like taking data from one and using disjoint unions of conjunctive queries to get data in the other. And this has a really nice story in terms of polynomial functors, because a schema, which is just a category, is just a polynomial comonad. So I don't have to like reinvent the wheel and like tell you what a category is from scratch make a DSL for that. You just make the DSL for polynomial functors and then define what a comonoid is there, or comonad, a comonoid in poly with a substitution product, and you're going to get categories from it. And then the functors from C to set, the actual data itself, is a coalgebra on that comonoid. And data migrations are co-modules between these things. Again, this might sound fancy, but you just have to, it's like you can follow your nose once you know what those things are. You can just implement them without having to understand data migration at all. You just implement by co-module, which is something you can look up on NLab. And now you know that everything you're writing is going to be about data migration. So often in computer science, databases are considered ugly, but the math here is really just very clean. It's about comonoids, coalgebras, and comodules. Things that have definitions in every monoidal category. Dependent type theory is what proof assistants like Coq and Lean are based on. And the idea is that the values of one type can depend on, a type can depend on the values of another type. So for example, a category is a dependent type because it consists of a type of objects, and then for every pair of objects, a type of morphisms between them, and then more stuff, identities and compositions and rules, depending on all those previous things. And then following Steve Audi, there's a tight connection between polynomials and dependent type theories. So you can model a dependent type theory as a Cartesian polynomial monad, a monad in poly, or a monoid in the substitution product of poly, and a pseudo-algebra for it. So if you remember back, I said that a polynomial, you can think of it as types and terms. The base of it or positions are types and the directions are terms. If you think about it in those terms, a type here in this composed polynomial is a type of M, a type, and for every term of it, a type. So that's a dependent type of size, kind of height 2. And you could have M triangle M triangle M. Now it'd be kind of a dependent type of height 3. And then the multiplication map for the monad tells you how to realize every kind of compound type, a type in M, and for every term of it, a type in M, as a single type in M. So M as a polynomial monad is a kind of system for sigma types. That's what polynomial monads do. And pi types you can get using pseudoalgebras, or if you move to a kind of higher level, you can use what's called a distributive law on this monad over itself. But the point is that the type forming and the term forming rules of dependent type theory arise just as the axioms of what a monad is, or what a distributive law is. So the high-level language of proof assistance has semantics in poly, or at least something very close to poly, like something derived from poly. Okay, all of that was just to tell you that a lot of parts of computer science, whether they're like state machines, or just basic functional programming stuff, or categories, which are becoming increasingly relevant in computer science, or databases, or dependent type theory. I could have told you about effects handling or rewriting, that all these things are just kind of native structures within poly, that poly is all about getting the piping and plumbing right. But now I'll try to move into artificial neural networks and other things using something called org. So imagine a category like set, except where the morphisms are dynamic. So you have two sets, and a morphism is just, instead of a morphism being a function, it's a machine. And in its current state, it's giving you a function. But as soon as you put an input in, it not only gives you the output, but it updates to a new function. So it's like a morphism. It's like a function between sets, but that function is changing based on what you put into it. So I think when people imagine like a function as a black box, usually you just put something in, you get something out, and stuff like that. But imagine that based on what you put in, you get a new function. Like maybe in some kind of bureaucracy, you might think, if I do the same thing repeatedly, I'm going to get the same answer. But it's not true, because every time you do something, it changes how that bureaucracy sees the world. So this is a very common sort of thing. And it's just not something that math usually thinks about. But it's pretty easy to think about in terms of polynomial functors, or just more basically in terms of Mealy machines. The internal hom AY/BY is some kind of polynomial, and a coalgebra on it is a Mealy machine. So we've talked about coalgebras. And a Mealy machine is just a machine that has an internal state. And for every internal state gives you a function from A to B, as well as for any input A, a new state. So it's a dynamic function. And so we can generalize this with arbitrary polynomials. And the resulting formalism is a setting for artificial neural networks and prediction markets and other things. So these are dynamic functions. They're functions that when you use them, it changes them. So how does this work? Well, the tensor product is closed. There is an internal hom for it, which we talked about before. And this closure turns out to be very relevant, because what is it? This closure is a new polynomial. It's this polynomial here. It looks complicated, but what is it saying? It's saying that a position or output of this polynomial PQ is a function from P to Q. So it's just telling you about functions from P to Q. It's like, here's one, here's one, here's one. And why is it saying over and over, here's one? Because you're using this thing. How are you using it? You're inputting a position of P, and you're inputting a problem in P, and a solution to its image in Q. Or you're inputting inputs in P and training data in Q. So you're like in neural networks, we'll be able to use these. These are what the reason we're here now is we're moving towards neural networks. So a position in this thing is a map from P to Q. It might make more sense if you had like a bunch of P's tensored together. That would be more like a wiring diagram. Positions of this thing are interaction patterns, basically like wiring diagrams from P's to Q. And a state machine or a Mealy machine or whatever, what we're going to be talking about, coalgebras on this thing are going to be things that output interaction patterns. They tell you different wiring diagrams and they change those wiring diagrams through time. And they input what's flowing along the wires, all the stuff flowing out of the P's and all the stuff flowing into Q and everything that creates in that box. So this is the basis for machines that adapt or rewire themselves, which was supposed to be towards this kind of idea of autopoiesis. Of course, I don't feel like we're at autopoiesis yet, but I don't feel like deep learning is autopoiesis. But you can feel that it's kind of in that direction. Things are adapting based on what's flowing through them. And that's what this is a language for. So they have some structure now. The current interaction pattern is the current output map there. But they can refigure it based on what flows through them. And that's just internal HOM. We didn't have to create that or make that special for deep learning. It's just what internal HOM is. So we're about ready to define this category org. If you want just some basic polynomial facts in any monoidal category, although monoidal closed category, although I'll be using notation from poly, one would have maps from the identity to PP, internal HOM PP, and from internal HOM PQ, tensor internal HOM QR to internal HOM PR. One would have maps from internal HOM PQ, tensor internal HOM P prime Q prime to internal HOM P tensor P prime Q tensor Q prime. And so, and lastly, so that's just true in any monoidal category, monoidal closed category, including poly. But also, I want to tell you there's a functor from poly to cat that takes a polynomial P to the category of P coalgebras. Those are the Moore machines on P. And that's lax monoidal. There is a kind of way of taking a P coalgebra and a Q coalgebra to a P tensor Q coalgebra. And once you have those facts, and I'm going to remind you, a P coalgebra is like a set S and a map from S to P of S. It's what I said before about Moore machines. Once you have all that stuff, we're like getting very close to defining org. And I just want to give you one last time intuition about PQ coalgebras. So if P is by to the A, then a P coalgebra is an AB Moore machine. If Q was internal HOM AY BY, then a Q coalgebra, I'm just saying, what is a coalgebra for these basic sorts of polynomials? Well, it's an AB Mealy machine in this case, or an AB Moore machine in this case. And the idea is that for every position in S, what is a polynomial? It gives us for every state S, it gives us a position of P, and for every direction, it gives us a new state. A morphism of P coalgebras is like a map from S to T with some kind of relevant equation, like some kind of commutative diagram. And it ensures that for any state S, it sounds complicated, like what do you get there? But in fact, the behaviors of S and the behaviors of F of S will be identical. There's almost nothing going on except that T can like collapse two states that act exactly the same, or add some states that S never can get to. But any state that S can get to, the behavior of that going forward will be the same as the behavior of the state that it goes to in T going forward, if you have a map of coalgebras. It basically just says any S behavior is a T behavior. So what is a PQ coalgebra? It consists of a set of states, or maybe you can think of them parameters like weights and biases. That's the set of possible parameters. And for every parameter, we get a polynomial map from P to Q. And not only did that, and this is kind of be how like the current weights and biases as a parameter that tells you how to take inputs and get outputs and how to do backpropagation. And not only that, not only do we have inputs to outputs and backpropagation, but we also have update, which says that if we're in a state and we have some kind of training pair of something in P1 and P of 1 and something, we have a training pair, some kind of input and some kind of loss, then we get a new state, a new bunch of parameters. So the bicategory org, the objects are the polynomials, very easy. The morphisms in org are the PQ coalgebras. This is a category of PQ, internal HOM coalgebras. So if P was this polynomial corresponding to these two tensor together, and Q was this polynomial corresponding to the whole system, then a PQ coalgebra would say that I have a set of states, and every state gives me a map from P to Q. Like this is one state that the controller is wired to the plant this way. Plant is wired to the controller that way. This would be one moment in this coalgebra. And then it would output these interaction patterns, and it would input what's flowing along the wires. So once you knew what flowed, you might be able to like this system, this coalgebra, would update this wiring diagram to give you a new wiring diagram. So it's a machine.
David,
yeah.
Just to let you know, we're at the full hour, but it should be fine to go up to 10 minutes longer. Just to
Thanks a lot, Bruno.
Yeah.
Okay, so this thing is updating its state based on what flows. And so artificial neural networks can be described in this language. Let T be the cotangent bundle of reals. So it's a real number is a position, and a direction is a cotangent or gradient vector there. Then what happens if you tensor it with itself? Well, you get the cotangent bundle of r squared. If you tensor itself to n times, you get the cotangent bundle of r to the n. So we just tensor this thing with itself lots of times. And then what we're looking for in deep learning is maps from tensor powers of t to tensor powers of t. By a map, I mean a coalgebra on this internal Hom. So it sounds complicated, but again, internal Hom is just something that you have in any monoidal flows category, and coalgebras on it or something you would have in any such thing. Or at least if you have some kind of action on like polynomials do on sets. So what does this give you in poly? It gives you a set of states or parameters, and for every state, a function from Rm to Rn, as well as a function that takes an input in Rm, a gradient in Rn, and gives you a new state and a backpropagated gradient in Rm. So we might call this backprop and gradient descent. That is just what this this coalgebra is doing, is a way, a coalgebra is a way of moving data from Rm to data in Rn, and moving data in Rm together with a loss on Rn to a new state, a new bunch of parameters, and a new loss in Rm. So there are many such coalgebras, but one of them, the one we care about, is that the carrier of this coalgebra, the set of states is, a state is a dimensionality of the parameter space, a function from the parameters times their inputs to the outputs that's differentiable, as well as a current parameter. And then the state is updated by a training pair to give you some kind of new state. So what I want to say, though, is that org, this category org, not only gives you artificial neural networks, but also prediction markets. It's just a different polynomial. You can run the same idea again. So whatever you like about artificial neural networks, well, one thing you like about them is that they work. Another thing is that they're pretty easy to implement at the end of the day. That doesn't mean it's easy to find the right architecture. What that means is it's easy to understand what gradient descent and backpropagation mean and how they are stitched together using architectures. And that's what the polynomial functor formalism lets you do much more generally. So for a prediction market, imagine that there's a finite set of outcomes, and each participant outputs a prediction function. They say, oh, I think it's 30% likely that this team wins and 70% likely that that team wins. Like you get into what they call Bayesian hell if you allow somebody to have 0% chance on something, because then the entire system could blow up if everyone simultaneously happened to pick a 0%, like something that didn't actually occur. But forgetting that for a second, because that's just a division by zero thing that people often don't even write down. So I'm just being careful here. So what happens is every participant outputs a prediction about what's going to happen, and then receives the real result. And it's compositional if we assign every predictor a trust or amount of wealth or trust, relative trust. So if we have a bunch of predictors, then the relative trust is, you have 50% of the wealth, or I trust you 0.5, and that other guy has 20%, and that other person has 30%. That information is the relative trust. So you have a bunch of predictors, and what you get is a new predictor by just multiplying their prediction by the trust that you have in them. So I'm not going to go through this because I'm low on time, but basically you have a bunch of predictors, and you can put them together to get a new predictor, And the idea is, again, just using these PQ coalgebras, or P tensor n comma P coalgebras. These are machines that take a bunch of predictors and give you a new predictor by kind of aggregating all the predictions, as well as give you, for any outcome, a way of telling the outcome to everybody and updating their wealth based on how well they did, how well they predicted it. And so you'd use Bayesian update to update their wealth. So I'm just going to kind of, use Bayesian update to update these coalgebras. Like the coalgebra, the coalgebra will consist of a way of taking predictors and getting a predictor, as well as a way of taking outcomes and returning them, as well as a way of updating the process itself, the wiring itself, or the interaction itself, adapting the system to learning about how these predictors work in the real world, how well they actually do, is updating how they are being combined and aggregated going forward. And that's exactly what deep learning is doing. And a common feature is that in both ANNs and prediction markets, you have a certain polynomial. For deep learning, the polynomial is the tangent bundle on the reals. And for prediction markets, it's predictions where you receive the actual outcome. And in both of them, we look at certain internal HOMs. For artificial neural networks, it's T tensor M, T tensor N coalgebras. For prediction markets, P tensor N, P coalgebras. And these, in both cases, we have these coalgebras, they're state machines. The states are parameters here, or trust levels here. In artificial neural networks, we use the parameters to output a new function, whereas in a prediction market, you use trusts to output a function from predictions to predictions. And the artificial neural network updates by gradient descent, whereas a prediction market updates using Bayes' rule. But they have one more thing in common, which is compositionality. And that is that the same formula holds regardless of M and N, and they're stable under composition. So if you compose a bunch of artificial neural networks side to side, end to end, or in parallel, you will get another artificial neural network. And same with a bunch of prediction markets. And so basically, a dynamic organizational structure is a categorical structure enriched in org. So a dynamic operad is an operad enriched in org. The dynamic monoidal category is a monoidal category enriched in org. And so these were defined in a paper with Brandon Shapiro, and prediction markets form a dynamic operad, and artificial neural networks form a dynamic monoidal category. It's a categorical structure, operad or monoidal category, where the morphisms are changing in time. The morphisms, when you use them, they update or they adapt. So the dynamics are stable under series and parallel composition. And basically, for example, for artificial neural networks, it's the chain rule. So what I'm saying is that you can generalize this idea of chain rule far beyond artificial neural networks. For example, prediction markets have a kind of chain rule. They are dynamic operad. That means that there is some kind of, whatever the chain rule is doing for you in artificial neural networks is also happening in prediction markets. And this is categorified using what is called dynamic organizational systems or structures, dynamic operads, etc. So to conclude, polynomial functors have a lot of ready-made structure for computer science. It's the most highly structured category I've seen, and full of lots of surprises like comonoids or categories. And org is really simple to state there. It's got objects that are the objects of poly, and the homomorphisms are the PQ coalgebras using the internal HOM. A dynamic category is a category enriched in org. It's got ordinary objects, but it's got dynamic morphisms that change based on what flows through them. And so you have dynamic operads and dynamic monoidal categories and all sorts of things like that, just defined as monoidal categories or operads enriched in org. There are lots of examples. So we talked about artificial neural networks and prediction markets today. There's also a model of Hebbian learning that Sophie Lipkind and I came up with a few months ago, which is a dynamic monoidal category. But if you find any, please let me know, because the open question is there a dynamic organizational system for something like autopoiesis or sense making? So that's it. Thank you.
Thanks, David. That was very interesting. We're now going to move to the questions, and so if anybody has a question, do feel free to post it in the QA, or if you're watching from YouTube, you can also post it there. So we're going to forward them here. So there's already a question from Matthew that was asked sort of at the beginning. So he's asking, are the properties of poly only true if it's constructed from set, or would they apply if poly was constructed from any topoi?
Yeah, toposes are very, will have almost exactly the same structure. I mean, what I mean is that I believe that everything I've said about poly, all those operations at least, will work in poly E for E a topos, or even a locally Cartesian. Yeah. So what do you actually need? Lots of different parts of poly need different things. So you need a topos. That'll be plenty. All you need for the basic thing is a category with pullbacks. But if you add coproducts, then you get, if your category has coproducts, you get more stuff. If it has products, you get more stuff. So the more structure you add, the better. The more of these structures you will have in poly. But a topos has all the right structures, so it should have everything I've talked about today.
Mm-hmm. So there's the next question from Sichu. Have you considered what basic neural network results look like, say, universal approximation theorems?
Yeah, to me, I hate to say it, but I find the universal approximation theorem very boring. I mean, even a one-layer neural network has that. And the point is that for me, there's nothing interesting about neural networks except that you can train them. And the universal approximation theorem has nothing to do with training. It just says, if I happen to know the right thing, then with a one-layer neural network, I could get, I could position the weights to be whatever I need them to be. Doesn't mean you're going to find it through training. So in answer, any of those theorems is, probably, it's like saying, could I get a great predictor? Well, yeah, if you had a set of predictors that happened to be exactly right for your prediction problem, you would predict it perfectly. But that doesn't mean you're going to be able to get there through a process. So I'm not a huge fan of at least that theorem, but that theorem does apply. I mean, these are not special deep networks. These are not special artificial networks or prediction markets. These are all of them. So, and more general than the usual class. So anything that's true of, like, if you have some class of neural networks and you have some theorem about them, that theorem will be true here too, because these are them. This is just a generalization of that.
Thanks. So while we wait for more questions, I have a question of my own that's sort of been permeating as I've been learning, I've been hearing about poly, and it's right. There's so many things that happen in there, and so much stuff. My thought sometimes is what I don't see in poly, what I feel like I would love to see in poly is this idea of sort of enforcing a certain kind of typing discipline. So of course we have types and we have morphisms and we have all of this stuff. Though sometimes I feel like when I study these processes that have a forward, backward parameters and all of these, sometimes I feel like I want to not have them live in different categories, but sort of enforce a certain kind of discipline where these are different kinds of things that become apparent. And here it seems like it's all sort of the same color.
Yeah,
that
that's
makes
right.
sense.
So there's something called, as I said, in any monoidal category, there is comonoids and comodules. If you look at, and if your monoidal category is nice enough, then you can compose comodules, and poly is. So if you look at poly with its substitution product monoidal structure, then as I said, comonoids are categories. And the bicomodules are data migration functors, but they really feel a lot like polynomial functors. They're just typed polynomial functors. So if you look at polynomial functors between even discrete categories, bicomodules between discrete categories, which are the comonoids whose carrier is linear. I know there's a lot of stuff I'm saying here, but all I'm really trying to say is that you can enforce this typing discipline by looking at the comodules between discrete categories. That will basically have lots of the types in those discrete the objects in those discrete categories will be types, and there'll be no morphisms between them. And then a bicomodule between two of those things will basically let you enforce the typing discipline you want. And then, of course, you don't have to use discrete categories. You could use more complicated categories. But I'm guessing that at first, at least, the typing discipline you want is just very basic and doesn't even need the bicomodule stuff. If you want a version that doesn't use those words, you could look at Gambino and Cox's 2012 paper, I think it was, about polynomial functors and polynomial monads. And so, yeah, you can enforce it that way.
All right, so the answer is to go even deeper into the theory of poly.
Just the comonoids and comodules.
Right. Yeah. Fair enough. I'll have a look. So there's another question. This may be silly, but the y in the notation for a polynomial reminds me of the fixed point combinator in lambda calculus. Does this intuition have any?
I didn't mean that. All I meant by that symbol was Yoneda. Y to the power s. There's a Yoneda embedding from sets op to functors from set to set, and that is y. Y to the power blah. I wanted the y because it was lowercase. I wanted all my polynomials to be lowercase. I don't remember what all the things I had, but like, why? Sorry, why? Oh no, I wanted it to look like algebra. I also wanted it to look like Yoneda, and I also wanted it to look intuitive in terms of just like, you know, positions and directions and things like that. So just kind of that's where the little y came from my point of view.
So it looks like there's a question from Andrew who's raised his hand.
Hi there. First of all, thank you so much for this talk. I learned a lot of things here, and I was curious. So one of the most ubiquitous architectures right now is, well, transformers and more generally attention mechanisms. And I was wondering if it feels like it should be really simple to say what cross attention is in this sort of context. And I was wondering if you or somebody else had kind of worked out what this definition should look like.
I have not. I think that it still should, like, it'll still fit into this system. For example, I mean, I know it's not weight tying, but like convolutional neural networks and recurrent neural networks, if you just think about it in terms of weight tying, all of that is easy to express in this formalism. But I don't know about attention. I've talked to someone about it before, and it looked like it was going to fit, but we didn't like actually do the math and figure it out. So that'd be a great project if someone wanted to try it.
Thanks.
So it looks like there is no more questions. So there's another question. There are some theorems about the convergence of the training of neural networks at infinite depth and width. And there's some links. I don't know if you can see actually the questions, David.
I haven't seen that.
Okay, right. So the question is, and have you thought about something like this in poly?
I haven't thought about it. Again, like in some sense, what this will let you do, what poly is letting you do here is if you make a system for poly, like if you make a type theory for poly, or you make you implement poly in Julia, or you implement it in Haskell or whatever, then you can you will just kind of be able to type out what a neural network is by a few lines. You'll say, like, you can kind of, in some sense, you can write the structure down very simply. I think Owen and I did it in about like 10 lines of Idris code. So, and then you can generalize to prediction markets. You can generalize to other things also. So the point isn't so much to get new theorems about how artificial neural networks work. It's to paste different neural networks together, or to connect them to a prediction market, or connection them to your calendar, or to put it all into a bigger ecosystem. At some point, as we get different chatbots like ChatGPT and whatever Google's doing, whatever anybody else is doing, and we have all these chatbots, we might want to connect them into, in series, in parallel. We might want to have who's talking to who change through time based on what they say. You might want them to connect to your calendar, to whatever. And so if you want to kind of plumb all these different chatbots together, or you want to plumb deep learning models together, or you want to make the deep learning model itself, you don't have to kind of plumb them outside of the system. You can make a single system where all of this stuff is taking place. So it's not so much about new theorems in neural networks. It's more about plumbing together different neural networks or neural networks with other parts of computer science, so that it's not just a completely separated thing.
And I think we can end with one last question, which I think builds on the fixed point stuff, which says, doesn't the Y terminology have the similar properties in allowing for recursive definitions, like P of A is defined to be 1 plus AY, A times Y for lists?
Yeah, so the free monad, basically the free monad on a polynomial functor is what gives you lists, or what gives you trees, or whatever sort of recursion schemes you want. And so free monads, once you have the free monad on a polynomial, you can get the initial algebra by plugging in 0 into that free monad. So like, or you can take the co-free comonad and get the terminal coalgebra by plugging in 1. And so you can get recursion using those things. You can get while loops get while loops basically that cycle through some process and have some if statement. And if it's satisfied, you exit, and if it's not satisfied, you loop again. All of that makes sense in Poly, and that's how I would think about recursion there.
Okay, at this point we're quite a bit over time. So yeah, David, thank you again.
Thank you, Bruno. And sorry for the daylight savings issue. I don't know, but thanks again for the invitation.
Yeah, there's so much interesting stuff here, so I'm sure this is going to be talked about. And yeah, I think this is a good point to just to end.
Okay, thanks.
Yeah.
Thank you, David.
Thanks, David.
Thanks. Bye, guys.
Bye-bye.